and graphically how to find your limits, and if a limit exists or doesn't exist. And we've been looking at, look, pointed discontinuities, which one can we remove, like right over it, and which one actually jumps over that we can't connect. So this is kind of a little bit of a worksheet just to pull everything together. If a function is continuous, that means you can put your pen down. I think I was telling you guys yesterday what a continuous function is, and among my students last year, this was their definition of continuous, that you could put your pen down and never pick your pen up. Your definition of continuous is there's no gaps. It's just every x in the domain is used, and there's no breaks here. So this obviously is not continuous. A good way to check is start writing, and if you have to pick your pen up to go here, this is not continuous. I have to pick my pen up and jump over that little open circle, but that part and that part is good. I don't know what. I can't, because then you change the look of my graph, right? If I have to jump at all or over something, it's not continuous. Now, the last couple days, we've been looking at these exceptions. We looked at this exception. This was your pointed discontinuity. That we said we actually have a limit as x. I can't use x equals to 2 over here. It's a function. Its value is this guy up here. But its limit is the one that it approaches from this graph. And we've been looking at your limits from a graph, right? We narrowed it down, we looked at it. We looked at it algebraically, didn't we? Factor and find your point of discontinuity and find your y value. So if we actually can fill this little circle in with a y value, what would that y value be? According to this graph, what y value would make me be able to fill in that circle? 1. So the limit, as your function approaches 2, would be equal to 1, right? Isn't this what we've been doing over the last couple days? Looking at the, from both ends, the left and the right. We did it graphically. We did it algebraically because we factored and reduced, and the factor that we took out was your pointed discontinuity. Then we plugged it in, and we found your y value, right? And didn't we confirm it on your calculators? So this is what we've been looking at. Then we found some that, like the lines came like this. They went here, and then they went here. And we said, did this have a limit? No. And I think I kind of told you, we call this a jump discontinuity. We have to jump from here to here. So that limit did not exist. So all I'm doing is pulling this all together so that you can remember back to graphing and solving algebraically. So to make something continuous, you have to do it so there's no gaps at all. Like this little section right here, it's continuous from here to here. I never have to pick my pencil up at all. I can start at the right and end here at, start at the left and end here at the right, and this little point exists in the middle. We also have, and I kind of told you a little bit about this the other day, sometimes you have a limit as x approaches a number, let's say it's 2, let's do this one, from the left, and as x approaches 2 from the right, from the negative side, from the positive side, they should meet at the same point. So sometimes you see it used with a negative and a positive. Okay. So these are things we've done over the last couple days. Here was one of your removable points. So we're just kind of calling this as you would in calculus. We call this a removable point of discontinuity if I have a limit that says I am approaching the same y value from the left side and the right side. Right? We did that graphically. We factored, we removed our factor, and we saw what the y value was going to be. We did it algebraically. So we call this a removable point. If you can technically fill this point in so that you can go like this, then it's removable. If you can't, then your limit, we said, did not exist, right? It didn't converge at the same point. your limit did not exist. We call this a jump discontinuity. And we had infinite ones, the ones without bound, because sometimes they just came up like this and they will never, never, never meet. They're without bounds. Something, a vertical asymptote, something that we couldn't factor out of the denominator, caused them, their end behaviors, to go up and up. And it usually was when we had your vertical asymptote. Now, the one problem that stands out is yesterday's problem. We had one of these. I forget if it was x plus 7 or x minus 7, but it went like this. This was a great problem. Because when we factored this guy,
So the one? I mean, it's one over that?
one, right, was 1 over this, right? This was our point of discontinuity. This was our point that we could actually find the y value for, remember? But this one was an asymptote. And that was not removable. It caused the ends to jump up like this, to go away from each other. So this one had a nice point of discontinuity and a jump, or without bounds, basically, a without bounds one. So one that we could connect and one that we couldn't connect. So these are what we've been looking at over the last couple days. The sheet that I gave you, was a nice example of a piecewise function. Just so that we can just kind of pull this together and see, how does this relate to what we did before? How did we make this connection to finding our limits, finding our discontinuities? How did we make some kind of connection here? Now, piecewise, if you remember, says this function uses this part of my domain. This function uses this part of my domain. Each one of these functions has an assigned part of its domain, right? That's how we do a piecewise.
There's graphs, right?
It's graphed over there.
Okay.
Yeah. Now, if you take a look at this function, this guy over here, is this continuous? Can I put my pen down and connect without ever picking it up?
No, you can't do it.
Because of this guy right here, and this guy I have to go over him, and this guy, and I can end there like that. So I have a couple of points that I have discontinuity.
Oh,
if you look at those points, I'm going to just erase this so you can see them.
But in this case, since they're
Is the
one
whole
has to be
thing.
closed, one has to be closed, and one has to be open for it to flow out.
Yeah, for everything to flow, everything has to be closed, and you have to not be able to pick up your pen.
Okay.
So, tell me at what value is this discontinuous?
Negative
When x is what?
At 0.
X is 0.
And it's at
1, 2, 3.
Okay, good. Very good. Now, let's just talk a little bit more. When x is 0, is this removable or not removable? Can I fill in that little point so that they will connect?
You can.
What would it, this and this?
Yeah.
Could I fill in one point and have them connect?
No.
No. So it's not continuous. This is not removable. This is called a what? A jump. Good. Not removable. There's no way I could make that connect. How about when x is equal to 1? It's removable. And if I could find its y value, what would it be? 2. So the limit as x approaches 1 is 2. Now I want you to notice one more thing. What is the value of this function? Oops, wait a minute. This is a little bit different from this. What is the value of f at 1?
What did you say?
It's
Wouldn't it
2.
one?
No, it would be 1.
How would it change?
Because you see this point right here? Isn't he filled in?
Oh, yeah.
So he belongs to this guy. Now, see the difference between a limit and a value?
So a limit, is it the difference because they're open and closed? Is that?
A limit can be closed as it approaches that point. What a limit says is, as I come up to that point from the left and from the right, do I come to the same y value. If I took this one right here, say I did it at 1.5, I'm still approaching this from the left and from the right. It would be that limit, whatever this, like say this is 3/4, it would be 3/4. This one, as I approach from the left and the right, you're right, my limit is 2. But the value of my function at 1 is still this guy because he exists. He doesn't exist in my limit.
So you're basically saying what's the value of like x at, or of that x number when you
Yeah.
choose the y.
Yeah. So because this one had a point that we could use. At 2, we don't have anything at 2. We don't have a value at 2 of our function. However, we have a limit at 2. The limit as x approaches 2 would be 0. The value of this function at 2 does not exist, right?
Gotcha.
But the limit says, as you approach this from both sides, what would this point be? If it doesn't exist and I converge at the same point, that's my limit. Does it make sense? The difference between a function value and a limit? What would my limit be as it approaches 3? Excuse me.
X equals 3 equals 0.
0. I'm looking for my y value that I can fill this in with.
The value doesn't exist.
Okay. This has a limit as it approaches from the left. It kind of stops, so it doesn't have one from the right. So there's your negative and your positive type deal. If you're approaching from the right-hand side, if you're approaching from the left-hand side. Okay? Just something that I wanted you to be able to put all the things we've done the last couple days to see what this means. This guy, is this continuous? Can I put my pen down and not pick it up?
No.
No. So it's not continuous. At what values of x is this not continuous?
1, 2.
Just 1 and 2? Okay. What is the value of this function at 0? When f is at 0? 1. What is the value of this function at 1? When f is 1? When x is 1? 1. Okay. What is the value of this function at 2? 2. You all okay with this? It's where it's closed, right? It still makes this a function. Is this whole thing a function? Yes, because doesn't it pass a vertical line test? One's open, one's closed?
Also, passing vertical line test is different from it being continuous.
Yes. Yes.
Um,
Yes. Exactly. So what we have are like, how do these things all relate? It's what this brings together. It's kind of a neat little way to do it. Now, you said this was not continuous when x is 1. Do I have a limit? As x approaches 1, here's my x of 1. As x approaches 1, do I have a limit? Do they converge to the same point? This guy
oh,
and this
at
one.
that so
At 1. Do I have a limit? Will it meet? Can I fill in one little y value to join those two things together?
no.
No. So my limit does not exist.
Looking for that point, right?
At this point. As I approach x of 1, right? From the left-hand side and from the right-hand side, do I approach it to the same y value?
No, it's different way values.
Different y values.
The last one we did too was also didn't exist.
The one on the other one too. When we approached it from two different sides.
That's off the graph you showed us how like there was two different numbers.
Usually you see it like this.
Yeah.
It starts like this and like this. Goes this way and this way.
Okay. And
So, yeah, say this is x of 1. Our value at 1 is this guy, the closed one. But our limit at 1 says, can I reach the same point as I approach 1?
it's technically not.
It cannot.
It's overlapping.
It's completely opposite. It doesn't approach the same number. Remember when we did these graphically, we had to look to see what was that y? It had to be the same number. Okay? So you have a value of a function, but you have a limit at that value. Okay? Now, as I approach 2, what's the limit as x approaches 2? what would that y value be that I could fill in? Here's my thing. I got to fill this guy in with what y value? 1, right? So my value of my function, remember your value is your y value. Your value when x is 2, I don't care about that point when it comes to a limit. He might be part of my function, but he's not part of my limit.
It's the one that's closed.
It's the one that I come to here, that I converge at. It's the one that I'm going to converge
Wait, I'm confused.
on. My limit is different than the function,
Right.
of the value of my function. My
But-
function,
So I said the limit was the one that was always closed.
no. We can have a point of discontinuity and we're going to close in on it. Remember we did these graphically. If they converge to the same y values, we're good. If they don't converge to the same y values, we don't have a limit. So this one and this one, will this converge at the same point? For a limit, we completely ignore that little random point. For a function value, we use that little point. See the difference? Okay? Alright? And these guys were just closed. We didn't have any problems with those. Let's try one more. Come on, hang in there. We'll get it. Oops. Alright. Alright. Is this continuous? Can I put my pen down and pick it up and trace it all the way through? No. We have some discontinuities. We have discontinuities. At what x value is this discontinuous? When x is 1 and when x is 2. Okay. Is this a function? Yes. Does it pass a vertical line test? Yes. It passes a vertical line test. So if I go like this, guys, if this is open and this is closed, God bless you. This one counts for what is the value at 1. This one. What is the value when f is at 2? 2. God bless you. Okay. When it comes to my limit, I want to work with the actual graph part of it. Remember, we graphed it, we solved it algebraically. So, when I approach my limit, when I come upon this guy from 2 different sides, if I'm looking at my limit as x approaches 1,
Okay, but it's just, there's no.
that does not exist. My limit does not exist. What do we call this? When it jump. This is a jump discontinuity. Jump. It cannot meet together. Now, you told me your other discontinuity was at 2. What is the limit as x approaches 2?
The one.
One. Good. Very good. That's the one I'm going to fill in so that I can go like this, right? I want to be able to write right across it. So this guy, is this removable or non-removable? He's removable. I can fill him in. He's called a point of discontinuity. He's just one little point that makes me discontinuous. But if I fill him in with that y value that everybody has as they're approaching this, then I can remove this. Good? Okay. It wasn't anything different. It's just another way to look at this in terms of here's a function. This is what we did with our functions. F at 1, f at 2, f at 3 versus here's a limit. As I approach this number, what do I approach it from? We did it graphically. We did it algebraically. Okay, questions? That's all I basically wanted from this one. Now, as x approaches infinity, I have a graph. And I have an asymptote right here.
All that?
No, I just want you to listen. I just want you to listen for a second. Sorry, guys, sorry. Okay. What's causing these two pieces? An asymptote. Good. I've got a vertical asymptote right here. I'm just bringing you back to when we did rational functions. We did these. And we're going to revisit them a little differently. So we had an x is equal to 0, a vertical asymptote. The vertical asymptote came from where? Does anybody remember how we found our vertical asymptote? The numerator or denominator? Denominator. It was one of the factors that we couldn't reduce, remember? If we reduced it, it became a point of discontinuity. If we couldn't reduce it, it became an asymptote. That's a vertical. This guy right here is called the horizontal asymptote. This guy also makes your ends behave differently, doesn't it? Look what it's doing to this guy right here. It's saying you can go all the way along this, but you can't cross over this. We did have a couple where it did cross over, but then it rode right back up against it again. Yeah, so it came like up against it a little bit. But this guides this along here. It kind of tailors your end behaviors. It tells it where should it go. This one also tells your end behavior where it should go, doesn't it? So your end behavior is going to approach, but not touch what value in this case? What is it going to approach? What y value? 2. Okay? So that's going to approach 2. Now, way back, when we found your horizontal asymptotes, we had 3 little rules. We had these 3 rules. But now we're just renaming them with limits. So, let me take this out of here and see if this makes sense to you. We said when the highest degree in the numerator is less than the highest degree in the denominator, in other words, I have this, x squared over x3. When the highest degree in the numerator is less than the highest degree in the denominator, we had a horizontal asymptote of y equals 0. This was one of our asymptotes we had. Now instead, as a limit, we're just going to say the limit is 0. Because isn't the limit the y value? So in this case, what is this y value? 0. So we're just renaming this with limits. Okay. We had this. Let me graph this back. We had a problem back in the day when we were doing these equations. And we had x squared divided by x cubed. Okay? And it looked like this. It looked like this. Right? Okay. Now, all right, listen. This is what we did a few months back. I said, if the degree in the numerator is less than the degree in the denominator, you had a horizontal asymptote of y equals 0. Okay? Now, we know that our limit is what happens to the ends now. So as my x value is approaching infinity, look where my limit's going like this. It keeps on going and stays there, doesn't it? Mm-hmm. What y value is it approaching? 0. So therefore our limit is 0.
Oh.
It is your horizontal asymptote.
So will it always be 0?
Well, we're just getting rid of the y equal sign.
Okay, so like if it was like x to the second over x to the fourth, would it be 0?
Same thing. It would be still 0.
See?
It's the same as your horizontal asymptotes. Okay? Now, let's try another one. Let's try the second rule. If the degree in the numerator is the same degree in the denominator, so say it went like this. 4x squared over 3x squared. Okay? We said, well, so hang on. We said the limit, well, let me make this easier. Let me make this a 2. We said it was this ratio. It would be y is equal to 4 over 2. Now, what this does is this. It just says, okay, just make the limit your ratio. Get rid of the y equals. It's the same exact rule.
But that wasn't 3, but it'd be going closer to 2.
4 over 3. We just say 4 over 3. If it was 4x squared over 3x squared,
4 over 3.
4 over 3. If it was negative 2x squared over 9x squared, Negative 2 over 9.
So
It's
what's the
just
all
your
x squared
ratio.
for?
Oh, okay.
Well, the x squareds have to be the same. It's when the numerator degree is
If they were
equal to the
different, what if it
denominator
was
degree.
4x to the second and then 2x to the third?
Then it follows your first rule.
Okay.
It's 1 less in the numerator.
Alright, so if it's the same, if it's different, then you,
It's going to be one of these, one of the 1 or 3.
you do
If it's the same,
the
it's
three,
a
if it's the same,
ratio.
then it's one. Okay.
Now, we had one more situation. We had, and I want you to remember this, we said sometimes the degree in the numerator was greater than the degree in the denominator. And in that case, we had no horizontal asymptote. But do you remember us saying if the degree was exactly 1 more in the numerator, we had a slant asymptote? Remember when we did your slant asymptote?
Yeah.
So this one had no horizontal asymptote. Therefore, if this is the case, it has no limit. The limit does not exist. So it follows exactly to your horizontal asymptote.
Does that have to be exactly 1 less or 1 greater?
No, it could be anything. But if it was 1 greater in the numerator, we then said you have a slant. Because you couldn't have a slant and a horizontal, because your slant couldn't cross over your horizontal. But we don't have to worry about that. All we have to worry about is
Is there an answer for that, or will you just say no horizontal?
you just say no limit exists. So this graph would look like this. If I did this, it kind of looked like this. Because don't these reduce down to y equals x? You kind of got rid of your exponent if it was 1 more, not if it was 2 more. But in this case, we have nothing to stop this. No asymptote. So the limit does not exist. As this is approaching, watch. As x gets higher and higher, I don't know where that's going. It's not approaching any certain number. It just does not exist. It's just going off into the distance. So your limits rules follow your horizontal asymptote rules because your horizontal asymptotes are y equals. So your limits are approaching your y values as x gets higher and higher. That's all it is. So let's take a look at a couple of these. I should have graphed them.
Oh, I did a birding.
You did them.
You have to graph it to find it even though.
Well, I should have graphed it just so that you could see what it looked like. This one graphs like this. It goes this way, then it went like this, then it went this way. What you guys are looking at are your end behaviors. Watch. As x is approaching this, higher and higher and higher, this is going to stay all the way here. It's never going to move. That's the highest x I'm going to get. It's still going to have the same y value. It's going to approach which value? 0. So let's see if this is true. When my numerator has an exponent of 1 is less than my denominator exponent of 2, yes, then my limit is 0. It had a horizontal asymptote of y equals 0.
Can you do number 2?
Mm-hmm.
It's just like a plus has nothing to do with
We
it,
don't
right?
care. You
Okay.
find your highest exponent in the numerator and the denominator,
So negative 2.
so therefore it will just be negative 2 over 3. Because what it's going to do is this. It's going to make a line here, and it's going to like bounce off here somewhere, or whatever way it comes off of this. This is going to guide this guy right here. Its end behavior, whichever way that happens to graph. Now, your last one says the degree in the numerator is higher than the degree in the denominator. Your limit does not exist. Now, I want to point out one thing. Notice how many terms are in all these rational expressions,
2.
equations. One term, one term, one term. Divide, one term. So, watch what happens in this next one. We have to make this guy into one term. So, we put this over 1. We say, what's the common denominator? X squared. So, 1, this guy needs an x squared. It becomes 4x squared minus 3. You have to get it into one rational function. Okay? So now, the degree in the numerator is the same as the degree in the denominator. So it's 4 over 1.
What's the word doing today?
You're doing the worksheet. Try and remember that these are your